Hello and welcome to today's lecture. As you can see in the slide, today we are going to be starting a new chapter. So this is chapter number 6 from the Koenig and Ritchie textbook, and this chapter talks about structures. Okay, so now we start with the introduction. So far in the course, we have already seen a number of different data types that C provides to us, and those are essentially integers, ints, characters, floats, and doubles. So what we observe is that the way we use them is we declare variables of a particular data type, and then we perform certain operations on those variables. So given below is a small program snippet in which we have declared three integers x, y, and z. And in the next line of code, we are assigning values of 1 and 6 to y and z. And in the next line, we're adding y and z and putting the result or assigning that value to x. And finally, we print the value of x. So again, to summarize, we have basic data types, and we declare variables of those data types. We assign values to them, we use them in expressions, and we can also print them out. Okay, so now let us talk about structures. So as you can see from the title slide, structure is essentially a complex data type. So what is the need for structures? Sometimes we would like to create our own data types, declare variables of those data types, and then perform certain operations on them. So these complex data types essentially are called structures. So as far as the definition is concerned, a structure is a collection of multiple variables, possibly of different data types, which are grouped together conveniently and appear under a single name. So again, to recap, a structure is a complex data type consisting of other complex or simple data types uh, put together and appearing under a single name. Where can structures be used? So structures have a lot of nice applications. One such application could be if we want to store records, let's say for students in a specific kind of database. So if we consider a particular student, so and ask ourselves which is the information regarding a student that we want to store. So we can have various kinds of information. We could have student first name, student last name, student ID, student branch, student CGPA, SGP address, etc., etc. So in that sense, what we could do is we could define a structure called student, which is a complex data type, and then each student would then be a variable of that particular data type. So for our program, we are going to be considering a simple example, and let us look at an example from computer graphics. So starting with something very simple, let's consider a point that has two different values, one for the x coordinate and the other for the y coordinate. Okay, so now what we are going to do is we're going to write a very simple program that illustrates the usage of structures. So the structure over here is going to be a single point. So it is going to have two member variables. One is a value of x coordinate and one is a value of y coordinate, and both of these are integers. So if you see the structure specification, we see that the first thing we have here is the reserved keyword struct, and then this is followed by the name of the structure or the name of the complex data type, which is point, and then within curly brackets we're just defining all the member variables that are part of a structure, and then the definition ends with a semicolon. So what we say is a point is a structure that has two integer variable members x and y. So now that we have defined the data type or the structure, now we are in a position to declare some variables of this structure or of this complex data type. So the way we declare variables is same way we declare variables for simple data types like int x comma y. So here we have struct point p1 comma p2. So everything is the same. The only difference is we have to precede point with the struct keyword. So this is to specify that the data type that we are talking about, which is point, is actually a structure variable. Now the next thing which we have is assigning values to these structure variables p1 and p2. So specifically we want to assign values to the x components of p1 and p2. So one option is we can write p1.x equal to 1 and p1.y equal to 10. So this is again similar to previous declarations. Only difference is we use a dot operator. So this will link the structure variable with its appropriate member variable. Okay, so note that the dot operator connects the structure name to its member variable. So to assign the values to structure variable p1, essentially you want to assign values to both the x and y components of p1, and the way that we do that is p1.x is equal to one value and p2.x is equal to the other value. So that is option 1. Another option for assigning values to structure variable is we can say point p1 is equal to 1 comma 10. So values separated by commas and enclosed in curly braces. So once again note that while declaring in p1 and p2, we need to specify that they are structure variables by using the keyword struct. So the language does enforce that. Not doing so will result in an error. So usage of this keyword struct is to distinguish structure variables from regular or non-structure variables. So now let us see this short program in action, or let us examine the code. Okay, so this is our first structure program. So as you can see that we are including two different header files. One is standard input output, which we have been using all along, and the other one is the math.h header file. So this will be needed for the square root function, which we'll be using later in the program. So now as you can see, first thing we do is we define our point structure or point complex data type. So we have the keyword struct followed by the name of the structure, and then within curly braces we have got the two member variables, so both of them are ints, and then finally we end the closing brace with a semicolon. Okay, so now our intention in main is to declare a variable of this point structure complex data type, assign some values to it, and use it in some calculations, and then print a particular value. So now as we see from main, in the first line we are declaring a variable of the structure, which means we are declaring a specific point, and what we're doing after that is we are assigning values to both x and y components or x and y member variables of that point. So what we have is struct a keyword which is mandatory, and then the name of the uh, data type, and then which is point, and followed by the name of the structure variables which we are naming p1, and then we assign 1 to the x component of p1 and 10 to the y component of p1. So note that this is equivalent to saying let's say that int x is equal to 10. So here point p1 is equal to 1 comma 10, but the difference is we have to add the structure variable. So in the next line we declare a variable called distance, and that is of a double data type. So what this distance will do is it will calculate the distance from this particular point p1 and the origin. So first thing that we do is we try to print the value of p1. So printing the value of p1 is equivalent to printing the x and y components of p1. So both of them are ints as we see in the definition. So that's what we're doing in the first printf. So next, now we can use this values of p1 and we can calculate the distance from the origin. So we're using the square root, therefore we have the math function, and then the expression is x square plus y square. So once again, we have p1 dot x into p1 dot x plus p1 dot y into p1 dot y, and because they are the x and y components are integers, and the distance has been declared to be a double for the precision. So therefore, we have casted all of these four values as doubles, right? So what it will do is it will do x squared plus y square, and take the square root and then store the result in distance. And then what we are finally doing is we are printing the value of distance, which is the distance of point P1 from the origin. So once again, to summarize, what we are doing in this very short structure program is declaring a point, defining a point to be a structure or a complex data type consisting of two simple member variables x and y, both being ints. And once we have this structure, then we are declaring a variable of that structure. We are initializing it with the x and y values. We are printing those x and y values for p1, and then the next thing we're doing is doing some mathematical calculating the distance of this point p1 from the origin, and finally we are printing that distance. Okay, so now based on the material covered previously, we know that depending on the associated data type and the variable, a certain amount of memory is reserved. So for example, if we are looking at a particular character, then for that 1 byte of memory is going to be reserved. On the other hand, if our data type is integer, then for one particular variable, depending on the machine, generally 4 bytes of memory is reserved. So this amount of memory reserved has an impact on the largest value that we can store. And we also know that if we want to determine how much memory has been reserved for a particular data type, we can use the size of function. So if we do size of int, we probably get 4 bytes, and if we do size of char, we will probably get 1 byte. So in a similar way, we can also find out the amount of memory reserved by the machine for structure variables as well. So intuitively, the amount of memory reserved would be the memory that is sufficient for storing all the member variables of that structure. So to illustrate this, we can have a very short program. So here, if you see, what we have done is, again, we have declared a structure called point, and each structure variable, that means each point, will have an x and y component. So first we have the point structure definition, and then inside the main we have declared structure variable of data type point, and the name of the variable is p1. So next what we do is we assign the value to p1. So p1.x is equal to 0 and p1.y is also equal to 0. So next what we do is we use the size of operator, and the argument that this operator expects is that particular data type. So like int or char or float or double. So here the data type is what? So structure is the structure name is a data type. So it is point. And again, to signify that it's a structure data type, we have to add the word struct to it. So struct point will become the argument of size of. And then when we run it, most likely what we'll see is we'll see a value of 8. So that will be enough to store both the x and y components. Okay. So far we have assumed that as far as the structure is concerned, all the member variables of that structure are basic data types. So could be two ints, could be two floats, or some combination of those basic data types. But as such, there is no restriction on this. So we can have the member variables of a structure as themselves, they can be structure variables. So we call this a nested structure. That means we have a structure within a structure. So to show an example of this, let's again focus on graphics or geometry, and let's implement a structure called rectangle. So now, as you know, a rectangle may be represented by a pair of points, and those can denote the diagonally opposite corners. So now here's what we see. What does the definition look like? So struct, and then the keyword structure, and then the name rectangle, and then the member variables are both the diagonally opposite corners, which are essentially the diagonally opposite points. So now point P1 and P2, and that point structure we've already defined earlier in the previous slide, right? So here what we have is we have an example of a nested structure. So now again, rectangle also is a complex data type. It's also a structure. So we can now declare variables of that. So a particular variable of this structure would be a particular or a specific rectangle. So then later in the program, we can do something like struct and then rect and r. So which means now we have one variable of structure rectangle. And now when we want to assign values, so how can we represent this rectangle R in terms of values? So those would be the values of the diagonally opposite corners, diagonally opposite points. So which means values for P1 and P2. So here in this piece of code, we are assigning just the values for a P1 point. So how do we assign? So now what we do is r dot p1 dot x is equal to 1 and r dot p1 dot y is equal to 1. So now what we note here is instead of 1 we have two dot operators. So r dot p1 gives the value of point p1 of rectangle r, and that p1 itself is a structure, so which has x and y components. So then we add one more dot for the x component and one more dot for the y component. So like this we can assign the value of p1 for r, and similarly we can assign the value of p2 for r as well by saying r dot p2 dot x is equal to, let's say, 10, and then r dot p2 dot y is also equal to 10. So now let's look at a program that demonstrates this nested structure and also the other operations that can be performed on structure variables. So this program has been taken from the Kernighan and Ritchie textbook, and in the textbook it appears on pages 129 to 131. Okay, so now if we think about it, we know that structure is essentially a user defined or a complex data type that consists of a collection of multiple values or collection of multiple member variables. So at heart it's a data type, and we can have different variables of this complex data type. So now the next thing we need to look at is what kind of operations can we do on these structure variables. So again, if you go back and think about regular data types like integers or characters, and then try to recall what were the different operations that we could perform on it. So a lot of those operations, or a subset of those operations, are possible with structure variables as well. So one operation is a copying of structure variables. So when we say something like int x is 10 and then x is equal to y, so essentially we're copying the value of y into x. So similarly we can copy from one structure variable to the other. So given our previous example, we can copy one point to the other. Second operation is assigning to a structure variable as one unit. So here we assign the values of all the member variables of a particular structure variable. So for example, x and y components of a point. Third structure operation is passing a structure variable as an argument to a function. So once again, if you recall from the earlier lectures, if you have a function performing, let's say, addition of two integers, so the arguments are two integer variables values. So in a similar way, we can also pass a structure variable as an argument to a function returning a structure variable. So just like a function can return a regular variable or the value of an expression, function can also return a structure variable. Accessing structure variables using pointers. So this we looked at for regular variables, how we can manipulate them using pointers indirectly. So similarly, using pointers, we can manipulate the structure variables as well. So this is going to be used very heavily in data structure. So we'll just come to that and discuss. And then last one is initialization of structure variables. So this is possible with regular variables as well. Int x equal to 0. So just similar way, point p1 equal to 1 comma 10. So as you can see, there is a significant equivalence between the operations we can perform on structure variables and the operations we can perform on regular or simple variables like ints or chars. Okay. So now, as we discussed, what we'll are going to look at is slightly larger program that illustrates various kinds of operations that can be performed on structures and structure variables. So in the last slide, we had discussed that certain operations can be performed on variables of regular data types, like copying the value of one variable to the other, using the variable in an arithmetic expression, passing the variable to a function, returning a variable from a function, finding the address of the variable and assigning it to a pointer, and then using the pointer to manipulate that variable. So it turns out that all of these operations are possible with structure variables as well. So to illustrate some of these aspects, let us now look at this slightly larger program. So here, as you can see, what is happening is we have defined two different structures. Okay, so first structure is a point. So a particular point will have an x and y component. Okay, so that is one structure. The other structure is a rectangle, which again is a nested structure because the diagonally opposite points of that rectangle are essentially structure variables themselves. So each rectangle can be represented by its two diagonally opposite points, and each point in turn will have an x component, an x value, and a y component, a y value. So these are our two structures. So now we'll discuss a family of functions which perform certain operations on them. So the first function that we have is called make point. So now let's look at that. What is this function doing? So as it says on the comment above, this function takes two integers and it makes a structure variable out of them, and then finally it returns that structure variable. So this is an example of a function which is returning a structure variable. Okay, so once that structure variable is returned, then main can do whatever it pleases to do with it. So what are the arguments for this function? It's two integer values, one for x and one for y. So all it needs is values of x and y, and from those values it can create a specific point. So now, what is the return type for this function? So again, that depends on what kind of variable that this function is returning, or more precisely, what is the data type of the variable that it is returning. So data type is struct point. So that becomes the return type for this function. So we have struct point, make point, and arguments are int x and int y. So what is happening inside the function now? We declare a temp variable, so which again is a structure variable of point. So therefore we use struct point and then temp. And now, because temp is essentially a point, it will have both an x and y component. So we need to assign values to both of these. So so what we say is temp.x, to x as the x component of temp, is equal to the int x, and then temp.y is equal to int y. So now our temp structure variable is loaded, and now we can return that temp value. So this is one function. Now what the second function is doing is it's add point. So this time observe the function arguments. So here the function arguments are two structure variables. So we had already said that because structure variables are in many ways like basic variables or non-structure variables, so they too can appear as arguments in functions, or arguments to functions. So here what we have is struct point, that is again the return data type. Add point is the name of the function, and then there are two arguments, both of them being points. Okay, so point p1 and p2, and what the function does is pretty simple. It just adds p1 and p2 and returns a sum. So here what we have is, again, we need a temp variable for storing the result. So struct point temp, and then the x component is of course the sum of the x components of p1 and p2. So we get them as p1.x and p2.x. So we add them together and assign that to temp.x. So here is an example in which we are performing arithmetic with structure variables and also assignment. So likewise, we also need the y component, y value for temp, which is again simply the sum of y components of both points p1 and p2. So we write temp.y is equal to p1.y plus p2.y. So now our temp is loaded with both the x and y components, and now we are ready to return it. So these are, so far we have two different functions. One will take two integers and make a point out of it, which it returns. The second function will take 2 points, add them, and then return the sum. All right, so continuing with the same program, so we saw that we have discussed two different functions. One of them makes a point out of two integers, so it makes a point structure variable out of two integers, and the second function adds two variables of point structure and then returns a sum. Now the next function that we have is to determine whether a point is within the bounds of a rectangle or not. So note that we can specify a rectangle by the two diagonally opposite points. So note that the return type for this point and rectangle function is int, because it is going to evaluate to 0 and 1 value, so both can be used in ints. And as far as the arguments are concerned, one of the arguments is a point p and the other argument is a rectangle r. So here the interesting thing to see is both of the arguments are structure variables, but they are variables of different structures. So that is definitely allowed. So what this function will do is take in a point, take in a rectangle. So that rectangle will again have P1 and P2, and then it will determine whether this point P is within the bounds of the rectangle. So essentially what we are doing is from P1 and P2 we will extrapolate and calculate the perimeter of the whole rectangle. And now for the x value of P1 we need to check whether it is within the bounds of the x values of point P1 and P2. So what we do is r dot pt1 dot x gives us the uh, value of 0.1 for that rectangle, and r dot p2 dot x gives us the value of 0.2 for that rectangle. So what we have is, what we are returning is, if you see the expression, so what this is doing is p dot x is greater than equal to r dot pt1 dot x, and p dot x is less than equal to r dot pt2 dot x. So we have to check whether the x component of point x is within the bounds of the x components of p1 and p2. Okay. So, and a similar kind of check will be done with the y components. We have to check that the y component of p is within the bounds of the y components of 0.1 and 0.2 for the rectangle R. So if that is the case, if both are true, then what this function will do is, it is going to return a value of true, which most likely will be 1, and if it is false, then it will return a value of 0. So I would advise you to pick certain values of pt1 and pt2. So maybe pt1 you can pick as 1, 1, and pt2 you can pick as 10, 10, and just draw that with the x and y axis values, and then for different values of p, try to see whether the point is within the rectangle or not. So you can do a case in which it's within the rectangle, you can look at a case in which it is outside the rectangle, and just see what the final value of this long expression will come out to be. And if we also see the order in which this expression is going to be evaluated, then if we just go back and check our order of precedence chart, what we will see is that less than equal to and greater than equal to, they have a higher precedence than the double AND. So in this case we are fine. Okay, so then that is our third function. So we have different functions, one for taking two ints, making a point out of them. Again, to summarize, second one for adding 2 points, returning the answer, which is also a point, and the third for determining whether a point structure variable is within a rectangle R, which is another structure variable. So now that we have both of these, we have all three of these functions, now we can use them and call them from our driver, from our main program. So let us see what is exactly going on in main. So first thing we do is we create a specific point called P1. Okay, so we go struct point P1 equal to make point 11, 1. So what this will do is take two integers 11 and 1 and then assign them both to the x and y components of P1. So again, when we call make point with 11 and 1, what it will do is temp.x equal to 11 and temp.y is equal to 1, if you see from the previous slide, and then that is going to be returned, that temp value is going to be returned, and then here this will be equated to P1. So now just like with regular variables, we can do int x equal to y, so we can also do struct point P1 equal to point temp. So the effect of that is now for P1, the values are loaded. The x component is 11 and the y component is 1. So P1 has a value now. So just to test it out, we can print it. So we have printf %d comma %d and then p1 dot x and comma p1 dot y. So both of these values will be separated by comma and enclosed in brackets. So next thing what we will do is we will declare a rectangle R. Okay. So now again, as we had discussed, a rectangle is defined or can be represented by the diagonally opposite points. So those diagonally opposite points, if you look at the definitions, are point PT1 and point PT2. So now again, for both PT1 and PT2, we need to assign values, right, to both of these points. And note that we already have a function for that, which is called make point. So then what we need to do is r dot pt1 is equal to make point 0 0. So which means one of the points of the rectangle is at the origin. And in a similar way, we assign the value for point 2 pt2, and what we say is r dot pt2 is equal to make point 10 comma 10. So now what we have done is using that make point function. Now we have assigned values to both point 1 and point 2 of rectangle R. Okay. So now just to see whether this function worked, we can print out the point 1 and point 2 values, and note that both point 1 and point 2 are structure variables, so they will have x and y component each. So then how do we print that? We can print it using this particular piece of code, r dot pt1 dot x, r dot pt1 dot y, that is for the pt1 component of R, and likewise for the pt2 component of r dot pt2 dot x and r dot pt2 dot y. So hopefully it will print correctly. So now we've got a particular point P1, we've got a particular rectangle R. Both P1 and R have been loaded with the appropriate values. And now what we need to do is we need to call this point and rectangle function to determine whether the point is indeed within the rectangle. So if you see the rectangle that we have, it goes from the origin 0 0 all the way up till 10 10, right? And P1 which we have is of course 11 1. So at once you can say that the x component is going out of bounds because it's not between 0 and 10, it's 11. The y component, which is 1, on the other hand, is within bounds because that is again the y bounds are again 0 to 10. So what it will do is it should print point is not in rectangle. So it evaluates the expression. All parts are not true, so it will return 0. And finally, so what it will do is it is going to print the else part. So we're using it inside an if, and once we call the function, we will get a value of 0. So the expression inside if is false, which will result in the else part to be triggered, and that is going to print the point is not in rectangle. If you use a different value for P1, let's say maybe we can use 1 comma 2 as an example. So now in this case, of course, if we see that 1 is within bounds for x, it's between 0 and 10, the range for x, and 2 is also within the range for y, which is also 0 and 10. And so both are within range, right? And then so the final expression is going to evaluate to true, right? So p dot x, which is 1, is greater than r dot pt1 dot x, which is 0, and it is less than r dot pt2 dot x, which is 10. And similarly, this similar thing would hold for this rest of the expression. P dot y, which is 2, is greater than or equal to r.pt1.y, which is 0, and less than equal to r.pt2.y, which is 10. So in this case, a value of 1 or any other non-zero value is returned, which results in the if part to be true, and therefore point is in rectangle, sorry, is going to be printed. So again, you can run this, and you should be able to get the appropriate output. Okay, so a note on the programs. So all the programs that we have discussed today, so 3 in particular, so they have all been uploaded on the Moodle course webpage. So all of you are encouraged to download them, go through them, also to test them out. And then if you have any questions, you can send me an email. All right. So now we summarize what we have discussed in today's lecture. So today we have done an introduction to structures, right? So we can look at structures as user-defined complex data types. So as programmers, we have the freedom to create the kind of structures that we feel are appropriate, are required to solve the computing problem. So a structure is a user-defined complex data type. It consists of one or more member variables, which could possibly be of various data types. So one could be an int, other could be a char, third could be a float, fourth could even be another structure variable. So first of all, of course, we need to define structure variables. We start off with using the reserved keyword struct, and then followed by the name which we can pick, and then within curly braces we define one by one all the member variables, and then finally we end the definition with a semicolon. So after defining the structure, we can declare variables of that structure and perform operations on them. So just like we have the int data type, so the int data type has already been defined for us, so it's system defined, not user defined. So once the int data type has been defined, all we need to do is declare variables of that int data type, and then we can perform operations on those variables. So similar kind of concept holds for structure variables as well. Why do we need structures? Structures are very useful for modeling a bunch of real life applications, mostly involving databases. So for example, if you have a student database, each student can be modeled or defined by a bunch of different values: name, branch, hometown, start date of degree, etc. Even something like a Twitter tweet could be associated with or could be represented by multiple values: number of characters in that tweet, which user posted that tweet, what was the location of the user while posting that tweet, how popular is that tweet, which we can determine by the number of times the tweet has been seen. So for representing a tweet, again, a different kind of a bunch of values, a bag of values is required. So simple single variables are not sufficient for storing and manipulating these. So what the structure does is it allows us to take a bunch of different variables and sort of pack them together, pack them together, and give one name to them, right? So that they're very useful in that respect. We also saw that structures can definitely be nested. So it is not necessary that the member variables of a structure are of simple basic data types like ints, chars, and floats. The members of a structure can definitely be structure variables themselves. So we saw an example in which we have a rectangle structure, and which is defined by diagonally opposite points. So for each rectangle, we have 2 points which are the member variables, and each point is in itself a structure as well. Okay, so in fact, this concept is the basis of inheritance, which is frequently seen and used in C++. So the idea is that if certain pieces of data have already been defined, then instead of defining them again, they can just be inherited from the base class or base structure. So in fact, there are a lot of similarities between C structures and C++ classes. So again, it's out of the scope, so we won't be talking about them much. And finally, what we did was we discussed various kinds of operations which are permitted on structure variables. So just like we can perform operations on regular variables, we can copy them, assign them, have them as function arguments, return them by function. So all of those can be performed on structure variables as well. And we looked at uh, a particular program which illustrated all of these aspects, uh, where we had structure variables as function arguments. So structure variables were returned by function, and so on. So in the next class, we are going to look at some more of these permitted operations. So in particular, what we are going to do is we are going to look at how we can use pointers with structures. So all of that we are going to cover in the next class.